Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure to introduce Richard Zemmel, who's visiting us from the University of Toronto. I know Richard from when we were both postdocs in the Salk Institute, Rich. And he's done a number of things, always sort of machine learning, starting working with Jeff Hinton on machine learning for information theory and neural networks and unsupervised and supervised learning. And it's a pleasure to have him around. He's here actually for a month. This is about midway through his visit. He has given a number of informal talks, but this is his sort of more formal MSR presentation. So thank you very much, Rich.
Great. Thanks, Paul. Okay, so I'm going to talk about the problem of learning to label images. And I should say that this work has been done in collaboration with my grad student, Juming He, who is he's the one who's got some of these programs, these algorithmic ideas that I'll be talking about actually to work, so he gets a lot of credit for it. Okay, so the aim of image labeling is you want to take, here would be an example, you have an image like this one, and think of the pixels in this image. And you want to classify every one of these pixels into some set of labels. All right? So here's a simple example where there would be 4 different labels. Every pixel is either a hippo pixel, a water pixel, vegetation, or a ground pixel. Okay? Okay?
That just sums everything up.
Yeah. So and then generally you got this color coding scheme that will be used throughout the talk. So every pixel will be, this is the ground truth labels in this case, green for vegetation, red for hippo. All right? So the aim is to take any image, and obviously this label set would have to be much larger. This may not comprise all the labels in the world. And you'd like to take the image and classify every pixel. Right? So that's a big goal because buried in there is basically the problem of object recognition and segmentation. Right? You have to say for every pixel which other pixels belong to the same class as it does, and kind of what groups of pixels there are in this image, as well as attaching a label to them. Right? So it's a very hard general problem with many applications, including things like video surveying, where you take photographs of the land and try to figure out what's what on the land. Object detection, right? So here you may want to take a bunch of images and just say, well, give me all the images that contain hippos, or does this picture contain a hippo or not? Or things like content-based image queries, where somebody might query a database and say, find me all the images that contain hippos swimming, right? And so then you'd look for hippos next to water or something. So if you have a labeled image, you can do a lot of these tasks, a lot of these applications.
But most of the image retrieval only requires you to identify what is in it, rather than where it is.
Right. So
this is much more detailed.
So this is more detailed, but it could be useful for things like saying, find me an image of hippos in the water, for example. Then you'd have to know that you have hippo next to water. So that would be if you have a more detailed query. Okay. So our approach to this has this underlying motivation. It's probably very hard for you to see here, but if I gave you these little image patches and I said, okay, are these sky or are they water, right? You'd probably be pretty confused, and you might just throw up your hands and say, this one's water, this one's sky, this one's a little grayer, so maybe in Seattle that's more appropriate, I'm not sure. But then, if I showed you the whole image, you'd quickly figure out that this was actually water and this one was actually sky. So the issue is, where are we getting this information from? So what and how can we get that kind of information into our system? Right? So the notion here is that there's information from different scales that come into play. There's the very local scale in the image that just say, give me the information right around the pixel of interest. Then there's possibly some more global scale that's relevant as well. So let me give you an idea of, this is just a cartoon sketch of what I'm saying is that if you had to say what's the probability that this patch was water versus sky, right? Just based on that, you might almost say 60-40 to water, and for this patch, you might say 60-40 sky. All right, just based on the local patch, what would you say? Now, I'm going to incorporate slightly widen the patch a little bit and say, well, if we look broader than just the individual patch, we see that up above that patch, this is the patch of interest, there's brown pixels, right? And brown could indicate something like ground, and so typically you won't see sky above ground. So you might say, well, it's more likely given that information that it's water. All right? Over here, you see brown below, so the patch that's above ground could either be sky or water, depending on where you are in the image, but more likely sky. All right? So this is kind of at an intermediate range of information, beyond the patch, but not the entire image. And then there's information from the entire image that comes into play as well, such as maybe this pixel is slightly above this other pixel, or this patch is slightly above this other patch. And so then it's more likely to be sky if you're higher up in the image in general. Right? So the notion is here we have this very local information from the patch, slightly broader information from regions surrounding the patch, and then information from the whole image. And all that stuff is going to come into play. Right? So I think of those as multiple levels of context that are going to come into classifying your individual pixels.
Why did on the bottom right image, why did the probability of sky increase?
So these are all considered independently. So what I'm saying here is that just based on this information, we might say most likely water. Just based on this information, we might say most likely water, but still some chance of sky, just based where we are in the image. That's right. That's right. Yeah. So in general in the talk, what I'm going to be talking about is how to represent and learn this kind of contextual information that I'm discussing, and how to combine these different sources. Different sources meaning the different contexts. The whole image, locally around the patch, and the patch itself. Right? So our main idea is that we want to capture contextual dependencies at these multiple scales. And we aren't going to do it in any kind of hierarchical scheme. It's going to be a flat, redundant representation of the scale. So we're going to represent all scales kind of at the same level. That'll be clear when I talk in detail about the model, I hope. And we want to build a conditional or discriminative model. Given the image, we want to come up with a set of labels for that image. All right? We don't want to build a generative model of images. Our images are going to be very, very high dimensional, lots of descriptors for the image that would take a lot of representational power to do the generative side. We can save a lot by doing it discriminatively. And you can look at this work as extending conditional random fields, which have been used a lot for text and like text labeling kind of tasks, to images. All right? And we're going to be learning these contextual dependencies based on image statistics. And in this talk, I'm going to summarize two pieces of work that we've done in this area. So the first one is work from CVPR. It was published in CVPR last year, called multi-scale conditional random fields. You'll see we don't get any points for real creativity in our names. And the second flavor was a paper from ECCV this year, mixture of conditional random fields. All right. So let's talk with the first approach that we had. So the multi-scale conditional random fields. Here's our hippo image and the labels, the ground truth labels. And what we're going to do, again, is combine information from different scales. So the first scale that we're going to do is something that's going to just look at the information that's in this local patch, denoted by the little purple square there, and try to classify that pixel as one of a set of labels. All right? And how are we going to represent the information in the patch? Well, we're going to run a set of filters on it. And those filters are going to be looking for color patterns, edge patterns, and texture patterns in that little patch. We come up with a representation based on the outputs of the filters applied to the patch, and we learn some estimate of the label or a distribution over labels for that particular pixel I. All right? So that's a probability of Li, that's the label for pixel I, given the patch information X at pixel I. All right? Does everybody see that first component?
So what kind of feature do you use? The color?
Color, edges, and texture. That's an L. It might look like a 1.
Okay.
This is an L. It's a bold L. Bold L sub I.
Lowercase l or something.
That's right. Bold lowercase l sub I. Uppercase L is going to refer to the entire label field.
All right.
Okay. All right. Okay. The next level that I had was slightly more beyond the patch, the very local patch, but not the entire image, are things we're going to call regional features. All right? And here what we're going to do is learn patterns of regional features in the label field. All right? So here's an example of a type of regional feature we might learn. We might say, well, one pattern that occurs frequently here is that you'll have water pixels, blue, below ground pixels, brown. All right? So this might be one of a learned set of label features. We're going to learn a whole vocabulary of these. Okay? And those are going to be then combined. We're going to get some distribution over the label, this portion of the label field based on these features. And those are going to be combined with the information that we got from the patch itself. All right?
So the click you're applying is pretty big.
It's big. Okay? So, yeah, so we'll get to inference issues in a minute. But first we want to just get the picture. What's that?
And learning.
And learning, that's right. Learning and inference is a big question here.
Your label is per pixel or per patch?
So the label is going to be, there's going to be one label per pixel, but it's based on information around that, the patch surrounding that pixel. All right? Because again, it's conditioned on the image, so it could actually be, every pixel could be conditioned on the entire image, but we're going to look at, this part looks at some local set of, some local patch. And this is actually looking at just the labels in the region, right? It's not looking at the image. Then we have more global features, which can look for patterns at a bigger scale. And think of that as a template that says, well, often we get this co-occurrence of some pixels that say we have hippos in the middle with ground above and water below. All right? So that might be a kind of pattern that occurs frequently at a larger scale.
That's like an unconditioned probability distribution.
That's right. That's right.
So that's a sample from that distribution or something.
You could think of it that way, yeah. That's not quite how we're going to represent it, but that's a way to think about it for now. Yeah. So you can think of these we can consider these as label templates. We're going to have a whole vocabulary of them again that are going to represent context dependencies at these different scales, regional and more global. And all of them are going to be combined to give you a single distribution over the entire label field given an entire image X. Okay? So that's the overview of the model. So now I'm going to go into and tell you a little bit more about how each one of these work, unless somebody has a question about the overview. Okay, so the local image label mapping is going to be a very straightforward approach. We're going to take color, edges, and texture filters, run on this patch, give it as an input to a neural net. The neural net is going to have the number of outputs equal to the number of possible labels for a patch. Let's say there's 10 labels. So what you get out here is a distribution. So each of these units in the output will have a value between 0 and 1, and they'll sum to 1. So it'll be a softmax over the outputs so that you get a distribution over labels for that particular pixel. All right? So that tells you not only which label, you can say what label is most likely, but you also get a distribution. So you have some uncertainty information there as well. That's going to be important. All right? And that'll be just a simple, straightforward, trained MLP.
The way the picture shows, you've got color, edges, and texture, but then those are compressed somehow into a single value?
No. So that's just to give you an idea of it. So, there's a bunch of filter outputs for each of these. There's I think there's 128 dimensional input based on some concatenation of those filter outputs. Okay. All right.
The label prediction is for each pixel you copy this structure?
That's right. That's right. The same predictor is going to apply to every pixel. Yeah. We also have later, we have augmented that by including some information of where you are in the image so that this could take that into account and change the probability based on that somewhat.
And inside this structure you have no sharing?
No, it's just a straightforward whole. There's no convolution or anything like that.
We haven't talked about training yet, but presumably, are these locally trained? In other words,
so this part is just trained on, you take every patch from every image is a training instance. Okay, every pixel, with a patch as an input, you predict a pixel as an output. You aren't doing the same. patches from the same image are treated no differently than patches from different images.
We're not training this in conjunction with the...
Right, so I'll get to the whole model training. So right now you want to think of this as being trained separately, and then we're going to be combining them. Okay? Okay, the more complicated bit of this is what Paul was referring to as how we do the regional and global features. Okay, so that's a little more complicated because now think of the input to those as the label of different pixels. All right, so you have a patch, let's say a 5x5 patch, and you want to say what label patterns are common in those 5x5 patches. Okay, that's the kind of thing being represented in one of these label features. Okay, so think of that now as the way we represent that is you'd have a bunch of label variables, 25 if it was a 5x5 patch, but now each one of those label variables has, capital K, let's say for K different possible labels. It has an input that is one of, like a distribution over the K, or just one of those K is active, right? So that's the input to this little system. 5x5 or 25 label variables, each of which is a multinomial variable, is the way to think about it. And now we're going to have some hidden representation that's going to use binary variables. And each one of these hidden binary variables is going to be one of the learned templates. All right?
So these things are kind of probabilities, but you're not treating them as if they were probabilities.
Which things are kind of
the inputs, the label classes.
Right.
They're multinomials.
That's right.
So
we are actually treating them like probabilities.
Oh, okay.
Yeah, because the way this restricted bolts machine, but they're going to be in our during training. They're going to be observed. So the fact that they're probabilities doesn't matter. They're observed to be one of the K possible values.
So there's some sort of equivalence that some sort of a mean field thing or something, because those probabilities are really like the mean values that.
Right. Well, you'll see. Then during inference, you're going to. Right. So during inference, you're going to be doing you're going to be doing sampling. But you're going to treat so there's going to be sampling of the from these distributions during inference. Okay? So you are going to treat it like a multinomial.
Okay.
Okay? All right? But the basic picture to have in mind is that here you have the different labels at different pixels, right? A whole set of them, let's say 25, and each one of these hidden variables is going to learn encode a pattern of these. And how is it going to encode a pattern of these? It's going to use the weights that go from it to the 25 inputs. All right? So each weight vector to a hidden unit encodes a kind of label template and specifies a conditional distribution of the labels. And the way to think of it is, like, if this hidden unit is on, that predicts a particular label distribution. If it's off, then it doesn't make any contribution. Okay?
The lengths that you call weights,
yes.
Are they also lengths in the sense of a Bayesian network?
Yes. So they're... Well, so on here you can think of it as the conditional distribution of the label given that this is on. So it is just like but in this case it's an undirected model, right? So it's not that you're going to always condition on the output, generate the inputs. So it's more like a potential. Right? Okay, so let me give you a picture of those before I show the equation. I'll give you a picture of the kinds of things we'll learn. So these would be different label features. Here would be an image. And you could see that the regional features, for example, that these are regional features that are active or match well to patches of the image. So this is a regional feature that says there's going to be vegetation in one part of the image and sky around it. So here's an area of the image that's going to match to, right? Because there's vegetation, that tree with sky around it. Here's one that has ground or you can't really see too well, building with vegetation around it, right? So there's a few of these. So each one so for feature visualization, we're just showing the most probable class. So actually, a weight is defining a distribution across classes that are consistent with that for every pixel. So really here, I'm just showing the most probable class, but really you have to think of that as a full distribution across label classes for that pixel.
So just a review here. So you have this restricted Boltzmann machine,
yep.
which has output units. And you can look at the weights going into any one of those single units and ask, like, what makes this thing most
That's right.
likely? And is that what we're sharing?
That's what this is here. That's why I consider it like a template. Like, what does it prefer?
Because it has this simple structure, it's just one layer.
That's right. That's why it's this restricted Boltzmann machine, right? None of these guys are connected to each other. They're all just connected to the input. Okay.
And so you can look at the pattern of weights, which most
would cause that guy to go on.
Right. Right.
Okay.
Okay. And so those are these W's. So the equation of that is you have some joint probability, right? It's an undirected model, joint probability of L and FRA are these feature functions that say for each one of these feature functions, we're going to there's R different one of them, and they're copied over the image. So there is weight sharing on these guys, right? You're going to apply the same one at different parts of the image, and you're just going to take the product of those with the actual labels. So you can think of it as applying the weight as a template to the labels. And if they have a good match, then you're going to get a big output here, and you're going to have a probable match to the particular hidden feature. All right? And then you can now what you do, though, is you want to marginalize out that hidden feature. You want to say, well, if that hidden feature is on, it predicts a particular input. If it's off, it predicts a uniform. Marginalizing it out gives you this distribution over the entire label field. All right? Notation's a little tricky here because we have different feature types and we have sharing of the features. So that's what the R and A. But the intuition, at least, people should be getting is, it's like your standard kind of convolution network, but now it's set up as this undirected model, all right? And it has this other thing where the inputs are multinomials, right?
here you interpret each of
these hidden binary variables as a class. So either this patch belongs to this class or this class or this class, but could be interpreted as...
No, so it's not really. So we don't want to think of these as different classes. We want to think of them as all, each one of these different ones is preferring a particular pattern in the input, and they're all operating at the same time. So So in other words, the R that the pattern here is going to be conditioned on these. You're going to have some distribution over labels that's consistent with whichever guys are active up here. So think of sampling the binary variables here, and then all of the labels that are active, each one of them induces a distribution here, and you can think of the distribution here. That's consistent with those as just a product of the distribution of the active ones.
So do you expect your image to...
If you do inference and you learn what the particular ones are on for each patch of the image, do you expect them to be a lot of them on for a single patch, or just have mostly one?
Right. So that assumption isn't built in here at all. We don't have anything about sparseness or any kind of competition. It's just a product where as many of them can be active as the model wants. Right. Typically, there's a question of empirically, what do we find? We find typically that only a few of them will be active, right? Because they're generally incompatible with each other. But they can specialize to sub-regions of the image as well. So they can say, I don't care about this pixel, but I care a lot about these, and other guys can do the complement of that.
So you have to prefix the number of labels.
Yeah, so in this architecture, we're going to prefix the number of we prefix several things. We're going to say the number of labels, like the label set, like I called K before.
But you don't automatically identify what they are, hippo,
No, all that is going to be in our training data. The training set has all that pre-identified. We're also going to, in this case, the way I'm showing it here, we're going to pre-identify how many, or preset how many different feature types there are at every level, and also the architecture. We've done experiments where this is actually done in a boosting way, where we don't do that, and we just learn these incrementally, one by one, and the results we got are almost identical to what I'm showing here. So it gets rid of that aspect of having to pre-specify that model architecture. Okay. Then we have global label features that work much the same way, but they operate on a much bigger field. All right, and there's a little. So just to, there's one little trick here that we do, which is they don't operate on we have a subsampled version of the image. So then each one of these guys specifies the label distribution for a whole patch of the image, and all the ones in that patch are meant to have the same distribution. So that stops this guy from having to look at some huge weights that are the dimension of a very large patch of the image. Instead, it's a subsample patch. All right? So that's just a little trick there to keep it manageable. So the kinds of global features we learn are, that you have polar bears in ice. So this is polar bears are yellow, snow and ice is white. Polar bears covered by, so these are images from the Corel database that we just took of wildlife. And you get a lot of hippos amongst grass and sky, or hippos in the water. Those are kind of global features that we learned in this. Okay? And they're combined all as a product, and you get each one of these guys gets combined as some large product with a normalization term out here to give you a distribution over the label set, all right, for a given image X. And this is just a little snapshot of the structure. You have an input image. The local classifier, the MLP, takes a look at this patch and classifies it as a particular label. And then you got these regional features looking at overlapping patches shown in green here of regional regions in the label field, and global features that are looking at the entire image at a subsampled resolution. Right? And all of those are put together as a product. And now learning an inference. So start with the inference is that we're going to have the, so given an image X, we're going to just treat each pixel I and do the mode of the posterior marginals. Okay, so we're going to marginalize over all of the other labels and find for each, treat each pixel independently, find its most likely label. All right? And this can actually be done using an efficient sampling method, right, for computing these marginals because we have these hidden variables. But it's a restricted Boltzmann machine, so you can go sampling back and forth between the label field and the hidden features that we learned. All right? So it's a block Gibbs sampling scheme. And we've done various other approximate inference methods. Nothing makes a huge difference here. We've done loop EBP, mean field. Mean field doesn't work quite as well. Recently, after we went to ECCV, there was a paper actually Rick had several people had on inference in Markov random fields. People are looking at that, and one of them was on, the best results seem to come from tree reweighted belief propagation. So we tried that and initially had some great results, but that turned out to be just on a subset of the images. And when we averaged over the full set, it didn't make much difference. So learning is a real bear in this model, as you'd imagine. So you want to maximize the conditional likelihood of the true labels given the images. All right? And you have a set of parameters. Now we have all the parameters are all the weights to those hidden features. Right? So we're going to learn the MLP part offline and just keep that fixed. And now we're going to be learning all these hidden features, the regional and the global features. And we could do that using Markov chain Monte Carlo. And the gradient for every parameter is going to involve, taking the derivative of the log with respect to that parameter under the true distribution and subtracting from that the same distribution, the same derivative evaluated at the equilibrium distribution. So you'd have to sample this chain going from the label field to the hidden features and back until you get to equilibrium, and that would take a long time. So instead we use this trick that Jeff Hinton came up with called contrastive divergence. All right? And this is just a little picture of that. I mentioned this at an informal talk last week. But now we have a conditional version of this. Okay, so the way Jeff worked it out for an unsupervised version, and ours is supervised, and there are it does make a bit of a difference. So let me just. But the basic idea is that you start off with some label distribution, and then you have to sample from your hidden distribution given those labels. All right, so that's what this arrow indicates. You're going to sample from the binary features up here given the label distribution. Then given those binary features, you can sample from your label distributions conditioned on those, and keep going until you get to equilibrium. Compute your gradients at the equilibrium and compute your gradients at your true distribution. And the difference between those gives you your learning. But like I said, it'll take a long time to get to equilibrium. There's a lot of noise in there. So Jeff's idea was, don't go all the way to equilibrium, just go one step. Okay? And compute this, take the difference between the gradient computed after one step and the gradient computed at the data, and that will point in the same direction basically as what would happen at equilibrium. All right? It's a somewhat heuristic argument in some ways. It's not, you can't say it's actually doing maximum likelihood, but it works quite well in these kind of difficult models where learning with this is not very tractable. Right? So you can run it for more than one step. We typically run it for 2 or 3 steps, but that's the way our learning works. Okay?
So you're going to make one pass, or you just said 2 or 3 passes through the image,
Right.
starting off with what the labels that are the true labels.
Yes. So that's one of the issues that comes up in the supervised version of it as opposed to the unsupervised. In the unsupervised, you start at the, so this whole thing would be, there's no image down here. You'd be just observing this, and you'd start with that and make a few steps, and then look at, in our case, though, we have the label image, and then we have information that we get from the, let's say, the MLP classifier. That's like an initial label. All right? So what we've done work on in this supervised case is to say, well, what's the right way of training this? Do you want to train it given the true labels as your first step, right, and then run the Markov chain from there, or do you want to start it from the estimated labels that you get from your MLP? And I think, unfortunately, our idea of that you do better from starting from the MLP doesn't turn out to be true. And I think talking to people who work a lot on these things, they say, well, ideally it really shouldn't be true because you're, if you've got to, detail balance here. So the idea is that you don't want to, it shouldn't matter what your initial condition is in some ways here. Right? So that's really the point. And that you start at the true data and you want it to stay at the true data. What we were doing was starting at the estimated label and then trying to make it move towards the true data. So we had this extra term in there, but it didn't actually work any better. It didn't work worse, but it didn't work better. All right. So anyways, I should probably not spend too much time on that. We have a paper coming out on this general setup of supervised. So we've done this kind of labeling approach with these hidden features for in other contexts. So it works quite well. It's quite efficient. And learning turns out to be easier in the case where you have one-dimensional data, like you want to do parts of speech labeling. Right? So we've applied the same approach described here to parts of speech labeling where you just have a one-dimensional text input. Right? It works quite well in that case. And let me show you how it works here. We have a subset. So we have 2 different data sets. One is the Sowerby database, which is from the British aerospace database. And so it has rural and suburban scenes. This is the resolution we've used in 7 label classes, 60 training images, and 44 testing. And we also took a subset of the Corel database, African and Arctic wildlife scenes, in this resolution, again, 7 label classes, training, again, 60 and 40. And this is the summary of our performance. If you just run the classifier alone, that is just the MLP on every pixel, and you say, per pixel, what's the accuracy? It gets about 67% on Corel and 82% on Sowerby. All right? Now, if you add an MRF to that, you say, not only am I going to classify with the MLP, but I'm going to look at pairwise relationships between adjacent labels. All right? So do a bit of smoothing based on adjacent label patterns. This doesn't change much, and this doesn't change much either. All right? So that kind of smoothing in some cases fixes things up. I'll show you some examples in a second, but it also can get things wrong. So it doesn't actually help much. And this is our model, the multi-scale one. We actually get a boost up to 80% correct on Corel and almost 90% on Sowerby. So our hidden features are doing more than what you would get just from a straight little MRF. All right? Here are just some examples to look at. That same hippo one, these are test images. This is the hand-labeled. And this is our set of labels, our 7 labels. Rhinos and hippos are the same to this program. Polar bears, water, snow, vegetation, ground, and sky. And you can see that the classifier is pretty noisy. Right? It thinks that all this stuff is kind of water based on the texture and the color. This is, looking at a local patch. It can't tell whether it's snow or water here. So they see a lot of blue in here as well as white. And things like, in the backs of the hippo, there's some glare and so you get lots of blue in there as well. So the classifier is pretty noisy. The MRF, as I said, it smooths things out, right? It does this local smoothing, but sometimes it over smooths and decides that there's a lot of water on the hippo's back, for example. And the polar bear comes out full of vegetation, right? Now, our model looks a little better. Unfortunately, this is a split slide, but just have to try to remember what the image looked like. We still don't get the backs right. The glare isn't quite right, but it's much better than the original, and we do pretty well in these images. Okay, these are polar bears with vegetation around. And we also get a confidence measure. So we get an actual distribution. Remember, we get a marginal distribution for every pixel. What's the label of that pixel? So we can say, well, what's the entropy at that thing? We can look and see that we get uncertainty right around the boundaries, like you'd expect, right around the borders of the animal. And I'll skip the confusion matrix for now. There's information in there, but it's not too important. The Sowerby one is a much easier data set, mostly because it's British countryside and it's all vegetation and sky, basically. There's not much interest there. But here's like an instance where you have some road markings. All right, so some smaller things that'd be harder to pick out. The classifier does pretty well getting the markings, but it also misclassifies them as having cars on them for some reason. Something about the edges are car-like. All right, the MRF smooths this in the wrong way and gets a car for this, and ours gets fixes up the classifier in a good way. So you can think of what our method is doing is learning local features and regional features and more global features to kind of fix up what the MLP is doing. All right, and here just the confusion matrix shows you that the predominance of vegetation and roads, right? So if these add up to 100 in the diagonal, that 75% of it is almost road or vegetation pixels in Sowerby. Okay. So just quickly about related work, there's been we aren't the only ones who've worked on this. Tree structured models people have done for a number of years to try to get. So think of our is trying to get multi-scale dependency, trying to get dependency across longer ranges in an image. All right, so people have done tree-structured models for this. This was his work on it's dynamic trees by Chris Williams and colleagues. Was another example of people trying to get these tree-structured models applied to image labeling. But there wasn't much flexibility. These don't quite have the flexibility that we have with our learned features. These guys came up with something called discriminative random fields, but that was more on pairwise label interactions, not where you had a whole set of labels. Toralba and Freeman and Murphy have worked on this kind of thing as well, but their focus has been more on object detection. They've also had a lot of context issues and different ways of representing context in theirs, but the focus is on object detection rather than labeling whole images. And then text on boost was a recent paper at ECCV, the same paper the work I'm going to be talking about in a second, came up. So this was Microsoft people, Krivenisi, Sean Wynn, Jamie Schotten, who's a intern here now, working with Navoisha. They worked on something called text on boost and applied that to some of the same data that we had used in our paper, and I'll show you their results when I get to it in a minute. And they had a much more sophisticated, an interesting local classifier, better than our MLP. But they didn't really have a representation of context in the way we had with our local features and global features. All right. Okay. So some of the problems with this paper, with this approach, is that one thing is that it operates on individual pixels. So it has to work on fairly limited resolution images, right? So we had to downsample our images to like a couple hundred by 100 or so of that order instead of a full resolution image. So that's one problem. Another problem.
That's the label resolution.
Right, not
That's
necessarily on the line.
That's right. So we could have labels of entire kind of groups of pixels. That's true. So I'm going to get to that in a second. Training still takes a long time, even when we downsample a lot. That is in the order of days, like 6 days or so, to train up this model. And it makes it difficult to scale up to more classes. All right. So because of these things, we came up with a different approach to the problem. I won't spend as much time on this approach. I think it's a simpler approach. Running doesn't take very long at all. Inference in this model is pretty quick because computing the marginals is, Well, generally, you can think of the classifier as getting you a fair amount of the way there, right? And then you're just doing these maximum posterior marginals. It doesn't typically take that many passes of sampling to get there, to get to the equilibrium. So it's on the order of, let's say a minute or two for a given image. So our second approach to deal with some of these problems I mentioned, one is that we replace the pixel inputs with superpixels. Right? So this is give you an idea of what superpixels look like. Superpixels is, the basic idea is that you take your descriptors of pixels, like what I was talking about, the edges and the color and the texture, and you run some sort of clustering algorithm. In our case, we use normalized cut. And based on that, you come up with superpixels. All right? And superpixels means that the way we've drawn it here, this little boundary here means that all of those pixels now become one superpixel. And we have one feature descriptor for that superpixel. So our image, which, I forget what the resolution was, now becomes represented by something more on the order of, 20 by 20 superpixels, like 400 or so superpixels per image. So we have fewer inputs, in a sense, to our system. All right? Now the task is to label the superpixels. Right? And we over-segment, in the sense, so that we want to make sure that within a superpixel we don't have two different classes, because we'll never really get past that, because we're going to only label down to the level of the superpixel. So we would never be able to repair it if there were two labels within a superpixel. So we intentionally over-segment with the idea that the system will have to do the rest of the segmentation. But we're getting some sort of segmentation out of the superpixels. Right? So that's the first thing. And then we're going to have a different way of representing the three kinds of context I talked about. There's very local context, intermediate context, and global context. And for the local and intermediate, we're going to have just a context-dependent simple CRF. Basically, it's going to be the MRF one I talked about before, but with a context-dependent flag. So in other words, it's going to be the local classifier, the MLP I mentioned, plus just an MRF of neighboring superpixels. Right? But there's going to be a different one of those that's learned for every context. And I'll give you an idea of what context means in a second. So the global context is going to be based on the idea that there's a gist of an image. All right? So this is something that Toralba and Oliva came up with. This is images from their paper where they took a whole bunch of mountain scenes and averaged them in a way and said that this is like some average representation of all the mountain scenes in this image. Here's an average of beaches and forests and highways. The idea is that these are fairly different, right? And that there's a number of different ways people have proposed to capture this gist. But the idea is that there's some way you'd like to kind of separate out and just look at basic properties of an image and say, oh, is this a mountain kind of image or is this a beach kind of image? All right? So that's the same kind of intuition that we have that drives our model here, where we're going to have a global context switch. And within each context, we're going to learn a different model. All right? And what we're going to get is what we call a mixture of conditional random fields, where the mixture is now going to be over these global contexts. And a little picture to go with it. So here's our super pixelated image. We have a gating function that's going to say based on the superpixel descriptors, which context do we think we're in. We have a local CRF, or it's kind of simple CRF that's different for every one of those contexts. And then we're just going to combine them and get a single distribution over the labels for that image. All right? So it's a kind of a... Sorry?
What does the gating function do?
So the gating function is going to give you just some distribution over context. You're going to have some limited set of contexts, and now it's going to say, given what I see in the image, what's the probability that you're in context 1 versus context 2? Right? And it's going to gate the outputs of these guys. So each one of these is giving you a full distribution over the labels, and now you're just going to kind of average them weighted by the gating function.
So what the purpose of the gating function is to calculate the image-wide gist.
That's right.
Yeah.
That's right. And to classify it and say which context are we in. That's what the gating function's for.
Why not use that as a feature into the CRFs?
Well, because this is going to allow us to have different CRFs for different contexts. All right, so we're going to have, the idea would be that your probabilities of seeing, what would be an example? Let me see if I have a good example off the top of my head of, like, of some sort of local context, for instance, that you might have, that next to water you're going to have a fish is going to be different if you're in a water scene than if you're in an indoor scene or something. Or if you're in an office scene, the probability of seeing a fish next to water is very small. If you're at a beach scene or at a lake scene, it's higher. All right.
So the crafts themselves have these simple cliques. They're now it's back to a
That's
simple
right.
clique. Right.
That's right. So I'll show you pictures of what the CRF. So here's the CRF. So there's different bits to it here, but so I'll go through it one by one. So first of all, there's this idea. So now we have a. So this is like the factor graph where you say, here's the input of the descriptor of a superpixel, and now we have a label associated with that. And so we have a MLP that's going to say what's the probability of seeing this feature of that you're in this this is the label of the superpixel given the input. All right. So that's one component of this. So that's the same as in the previous model. There's a second component of this, which is the pairwise features, which just says, what's the probability of seeing these two labels next to each other, two neighboring superpixels, but also given that you're in a particular context. All right? So that's going to be different. The pairwise probabilities are going to be different for every context. And finally, we're going to have what's the probability of particular labels given that you're in a context. So in a beach scene, you're going to have a high probability of seeing things like sand and water, but not so much. But you're going to have a much lower probability of seeing sand in an office scene. All right. So you have an overall probability, a global probability of labels, given that you're in a context as well. All right. So that's our context-dependent CRF.
So if you split your data into the different types of
Scenes that they correspond to, does that mean you'll have trouble because you don't have enough data, say, to estimate correctly some of these probabilities, like sand in office scene? Like you've never seen that, so
right. Yes, you're going to have those typical kind of kind of undercounting arguments, or not. So you have to do some sort of smoothing to take account of that. Yep. But we aren't going to do the splitting at the context by hand. We're going to learn the context. Okay, so we aren't predefining what the contexts are. All right. So one other detail before I describe the context a little bit more is that we're also going to have some boundary probability come into that gates the pairwise features as well. So we're going to have something that says between individual superpixels, we have this way of kind of edge. Offline, you can have programs that analyze the image and say what's the likelihood that there's a boundary in between these two superpixels. All right. So, for example, we just took code off of the Berkeley group, Malik's group, where they have this PB that they estimate. What's the probability of a boundary between two pixels? And that's based on low-level, intermediate-level cues. And we use that as an additional input to this. So it says that now, so that we can have different pairwise probabilities based on whether there's likely to be a boundary in between those two or not. All right? So here's an example of that if there is likely to be a boundary, you can learn that between these two superpixels, it's consistent to say one is rhino and one is vegetation, right? So it's a high probability for one being vegetation, one being rhino, and not much of probability of them both being rhino across the boundary. And vice versa, if there's no boundary, you expect them both to be rhino. Okay? So we have that additional bit of information to kind of gate out the pairwise probabilities. Okay, so now we have this global context feature. Let me tell you about the context. Oh, sorry, I'll get to the context in a minute. The learning now is, again, lower bound of conditional likelihood, a little bit different than our previous one. We have the gating term in here, right, which just multiplies this log probability of the labels. And that's our learning criteria. And our inference, again, is going to be the mode of the posterior marginals, similar to before, but now we have this gating term in there as well. So we want to sum out over the context. The difference here, so let me do a quick comparison between this and the previous one, is that the contexts give us a lot of representational power, is that we have this clustering of aggregate label distribution. So we kind of divide, as you said, we kind of divide the data into subsets based on context. So then we can scale this up to, the idea is we can scale this up to much larger environments, because larger environments mean that you have different contexts. And so you're kind of having this, a different model in a sense for these different contexts. So the key is, to what extent can you really recognize what context you're in based on the image? And if you can, then you have the ability here to model very different and much larger image sets.
So before you had this global label, global variables that were modeling joint distribution of the labels, but they weren't tied directly to the image pixels.
Right.
And that is, you consider that a flaw, or because they're indirectly tied?
Yeah.
And they drive you to kind of, conclude.
Well, this one also has the global label thing, but it doesn't have the global labels that is separate for every pixels. It's more like the bag of pixels, right? So it's just saying that in general, pixels should have this kind of distribution in this context. But it doesn't specify that in the upper left there should have this kind of label, and next you should have this label. Yeah. In this one.
Okay, so it's like the gist that gives you a kind of a pixel-independent.
That's right. That's right.
I see.
That's right.
You could have had a template style sort of.
That's right.
Pixel
Could have in this. Right. So the trade-off always is kind of ease of learning. So this thing is really fast to learn, and it's getting a lot of that, I think, by having so the question is with what we have here with the different contexts, without the very specific templates, how far can we get? Okay? Because the learning is quite easy and the inference is quite easy here. All right? Because in parallel, we can learn the context-dependent classifiers. So we first decide what context that we're in, and we can learn the context. Okay, so here's the general scheme. I don't think I have a good slide for this. Yeah, I don't. Shoot. So we first have to say, okay, how do we decide what are the different contexts? All we do is we look at for every training image, we look at the histogram of labels in that image, and we do clustering in there. All right? So a context is just a histogram over labels in the entire image, like a bag of labels. All right? So think of an image as a bag of labels, and we do clustering in there, and that defines our context. All right? Now what you have to do is learn a context classifier. That is, given that clustering, now we can say for every image, what is the context of that image? We want to be able to classify it and say, here's the descriptors of all the superpixels in the image. Let's come up with a distribution over context for that classifier. So that's what we call for that image. We call that a context classifier. All right? And then we're going to learn separately the joint probabilities that I talked about or the pairwise probabilities for the context-dependent MRFs. Those can be learned given the context. Right? So once we've defined the context, we can separately learn the different components of this model. And then all we have to do, the only hard part in learning in this case is the weighting parameters for the various components. So I'm kind of missing an equation here, but this is going to be a product again of the various components, and each one of those is going to have a coefficient, and that coefficient we're going to learn by putting the whole thing together. But separately, each component is learned. So it's a bit like what I talked about before, where you think of what you're doing is you're pre-training a lot of this model separately, and then there's only a few parameters. There's like 4 parameters, it turns out, that you're training jointly in the entire model. So it's a very efficient learning one. So just quickly I'll go through and tell you the data sets. The same data set we had before, we call it Corel A. Corel B is just a slightly expanded one where we went up to 11 classes, and the same Sowerby data set. And now we want to compare the pixel-wise classifier, where we just do each pixel, superpixel-based classifier, a context-independent CRF, right, which is like what I called the MRF earlier. Right, so it's just one CRF per image. And then the multi-scale CRF is the earlier work, and our new one, the mixture of CRF.
When I think of a CRF, this is something which is being trained discriminatively to, there are potential functions in this thing which get adjusted to kind of, fix the errors of other potential functions, by reweighting.
Mm-hmm.
And maybe I missed it, but it sounds like you're kind of training up each of your potential functions separately, and it hasn't really been trained overall to give you the right distribution.
It's only it's only the coefficients that are trained overall. So
The coefficients which makes the difference here.
that's right. That's right. No, the coefficients that within one of the CRFs, that you're going to have to combine the MLP plus the pairwise CRFs,
And
the pairwise functions.
a couple of parameters.
Yeah, that's just a few parameters. That's right. In a sense, though, it's being trained discriminatively by, so the pairwise, like the MRF really is looking, it's based on the training data, so it has the image statistics in there. It's not trained discriminatively, though, to come up with the correct labeling for the entire image. Right? Okay, so this is what I was trying to show before, the learned context model. So for Corel A, right, if we give it two different contexts, it ends up learning the kinds of things you'd expect, which are, that one of our contexts had the kind of African one had a lot of hippos and water, and the Arctic one had more snow and polar bear. Sowerby had two different contexts that weren't that distinguishable, one that seemed to have cars and roads, and the other one that didn't. Again, this is just clustering on the label sets. In Corel B, we tried it with like 4. We tried these with a number of different ones. So I'm just giving you an example here, where we again had the hippos and rhinos in a cluster. This is a superset of that one, and it had polar bears in water. It also had ones with tigers. It's misspelled, and another one that had horses in it. Okay, so those were just the contexts that it learned. Again, just looking at the label, this bag of labels, and doing clustering on those. Right? So it learns those contexts in an unsupervised way. Then we have a context classifier. Given the image information, you try to say which context of these applies to a particular image, and each one of the contexts has its own CRF associated with it. And this gives you a sense of the accuracy. So Corel A is the old data set. So our per pixel classifier, Corel A was around 67%. The superpixel classifier does better, right? So we're getting information by doing the normalized cut. That does about 71%. The CRF, which is the single context independent CRF, gets up to 74%. And our old model got up to 80%, and the new one is like at 81. So it's not much better, but the learning, in fact, is so much faster. In this case, it learns in the order of an hour, and inference is much faster as well. So it's a much more efficient model here. The text on boost, just to give you an idea, they ran it on theirs, and they got about 75%. Okay? So we're outperforming those here. Corel B is an expanded data set where we have more labeled images in it, and we couldn't run our old model on it. It's too big for that. And we're yet at just over 75%, again outperforming these other ones. And Sowerby we do a little better than the other ones as well.
Is the new method is a little faster, correct?
Yeah.
As far as the accuracy, what is giving you the accuracy, do you think? Is it the superpixels? Is it the new global context?
Right, so that's why we did these kind of several different ones. So the superpixels is giving us some, but not that much. The superpixels over regular one gives us a bit of a boost. Then having the pairwise things gives us another boost over just the superpixels. So we're saying, so this has to be, the difference between the green and the dark brown here has to be due to the context. That's the difference between these two. So really, no, forget the old method. This is between the CRF, which is a global single CRF built, or kind of, it's everything in this, it's this model where there's one context, right? So the mixed, the old model versus the new one is a little bit of a harder comparison, because the old model, is also built on this same classifier down here, right? And it goes up to there based on these experts, but these experts have different sorts of information that's a little harder to compare. So, yep. Oh, and I'll skip this. So we also can think of this as doing, if you wanted to run this for segmentation rather than classification, we have a metric where we say, well, for a given pair of pixels, throw out the label and just say which are pixels in the same class or different classes, right? And how well do we do on that task, okay, compared to other segmentation algorithms, all right, like mean shift and other ones. We do quite well, all right? So to wrap up, I'd say the contributions here, the second method I talked about I think of as a general learning framework for classifying regions in these images, because now we can scale up to many more images, many more classes. In fact, trivially, we combined the Sowerby and the other one, so we then went from 11 classes to 18 classes and maintained this. The performance was the average of those two performances because they were easily recognized as being in different contexts. So the extent to which, so a limiting factor here clearly is going to be the extent to which contexts are discriminable. But in any case, we have think of it as extending the standard CRF to a mixture model. All right, that's one thing that's being done in this second model. And we have a very modular, efficient training method for this approach. The first model I talked about, I think of as a novel learning algorithm and architecture for structured outputs. And like I said, there's broader applicability for that. Things like parts of speech labeling that we've tried it on, one-dimensional tests.
Part of speech labeling.
So it's under review at PAMI. And some of the issues that we're looking at now include, trying to have more and more data is always an issue here. You want to have, expand the number of images, and so it's an issue of getting enough labeled images is hard here. Another thing is we want to, scale up our label set to go to many more labels to really look at, making this a more realistic thing. So, and I think given the new model and the speed at which it trains, I think it's now becoming practical. It's really a question of getting the data, labeled data. And currently we're looking at ways of including some shape information, because there's nothing in here about shape. That's it.
So one of the things that we find CRF when applied to speech, some area they're working on, is that it actually allows you to define the features which is a function of both input and output. Mm-hmm. Whereas a generative model or the hidden model couldn't do that.
Right.
So in your case, your feature is still strictly the input.
Well, so we have, so we don't have, so yeah, we've actually done some of that. So it's true, we have the MLP you can think of as a feature of the input and the output, but it doesn't have joint outputs and an input like a standard CRF, right? So we've looked at that in this model. So in the boosted one I talked about, we actually boosted where we want to have local features that also depend on the image itself. We didn't get any improvement in performance, though. But it's certainly within there's nothing in this model that prevents that. It's just we haven't found it actually to be that useful.
So for the speech work that you just talked about and that review, the fact that you
so there we did find it improved it. There's a dimensionality issue there, right? So so one thing is that the input representation is very high dimensional per pixel in a sense there, right? Because you have all these different features. And the issue was now you have weights, or now you have parameters for all of those plus all the different parts of speech. So it's a real dimensionality issue. So for instance, someone else who tried to do these higher order things, so Andrew McCallum and some colleagues did ones where they try to do, so I think of this as capturing higher order dependencies. The first thing I talked about is really looking at higher order or longer scale dependencies in structured outputs. And not too many people have actually done that. The ones who did, so the Andrew McCallum was an example where they basically kind of hand-tuned that and said, okay, we're just going to have a few of those, and they're hand-tuned. So it's a difficult learning problem. Any other questions? No.
Great.
All right. Well, thanks.